Hi, everyone. I'm just going to wait a couple minutes before we get started.
Hey, John, should I try sharing screen?
Okay, I'm gonna just introduce. We're gonna get started. I'll introduce you, and you can share your screen. Yeah. Okay. So, hi everyone. Today we are pleased to introduce Yanou, our very own, who's going to be giving the colloquium today. Yanou obtained a PhD from University of Michigan. She went on as a postdoc researcher at Harvard and University of Maryland, and then became a senior research fellow at the Perimeter Institute before joining us as a faculty member here at UCR. Yanou, as most of you know, is a leading expert in the standard model of particle physics, particularly at the interface with cosmology and astrophysics. And her work has been very impactful in various big collaborations, such as, the LHC and June and LISA. She's got various leadership roles in the community, organizing major conferences and on decision-making panels for funding agencies like the DOE and NSF. And today, she's going to be telling us about the dark side of the universe with a highlight on using gravitational waves. So, Yanou, please.
Okay, so hello everyone. Thanks, John, for the introduction. So today, I want to tell you about my recent work on probing the dark side of the universe with new avenues, with a highlight on gravitational waves, but I also talk about other approaches. So before everything, I want to acknowledge my collaborators at UCR. This is in alphabetic order. Barry and Simin, who are wonderful colleagues. Chafeng, who's my student, who has been doing excellent work. Ren Huo, who's a former postdoc at UCR, now faculty member in China. And Martin, who's a Simin student, but we work on a project together. And Michael, who's my first graduate student, he did very well here. And just this September, he moved to his postdoc position at Triumph, a leading national lab in Canada. So he's well on his way to advance to the next stage of his academic career. Okay, so let's start. So first, I want to introduce to you the big questions that I am after about our universe. First, there are the deep mysteries about the matter in our universe actually comes in three folds. So in our department, first about dark matter, in our department, we have heard a lot of talks on this subject, including Philip's talk last week. So I'm not going to spend too much time here explaining this, but the main point is that dark matter, there's overwhelming evidence for the existence of dark matter, and it certainly demands new physics beyond the standard model. Now there's also this what I call the dark secret of the visible matter or atomic matter. This is about the origin of matter-antimatter asymmetry, or so-called Biogenesis. So this problem is no less significant as the dark matter puzzle. If we think about that the stars and our own bodies are made of a visible matter, the baryons, but so far we still do not understand this where the cosmic baryon come from. This is the question about where do we ourselves come from, and embarrassingly, we also do not know the answer. On top of these two, there's also this very interesting similarity between dark matter and baryon abundance today, which is quite remarkable considering that dark matter and baryons interact quite weakly today. So is this a mere coincidence, or maybe more interestingly, could suggest a deep connection between the two in the early universe? Now, another big puzzle that I am after is what happened during the first second after the Big Bang. This is also called the primordial dark age. So from our current understanding about our cosmos, the earliest data point we have is at the Big Bang nuclear synthesis time, which is about a second after the Big Bang. Then the CMB light, our best precision tool so far, was emitted long after that. Well, what about the first second that is before the BBN time? We do have a standard cosmology theory, but many of those assumptions that still need to be tested by experiment, and there are many unknowns. Now, you may wonder, how could this 1 second short time be of significance considering that our universe is billions of years old now? So the key is that if we put aside our human intuition about how short a second is, but instead look at how much the universe has expanded during this first second, or how much the temperature has evolved, cools down during this first second, you'll see the gap is quite significant. It's up to 20 orders of magnitudes of unknown. Now you may also wonder, but why do we care about such a remote past history? The key is that this era is very critical. It holds the key to big fundamental questions. For instance, the essential dynamics of baryon and generated baryon asymmetry should be established during this first 1 second. And also the seed of cosmic structure today arise from dynamics in this the very early epoch. So better understanding, so probing the primordial dark age would be very important for us to better understand and better predict current day observations that may lead to new physics discovery. So in my research, I endeavor to propose and explore new approaches to tackle these big puzzles. This include expand theoretical horizon by promoting new mechanisms. And this is a timely effort because many of the existing solutions, paradigms, are being challenged by the experimental data. In addition, I also work on identifying new phenomenology, new experimental search strategies to accelerate discovery. This is also particularly timely as now we're in the era of rich incoming data from many frontiers. So the research I will tell you today coherently cross 3 frontiers of high energy physics. Energy frontier related to say the LHC collider physics, intensive frontier, in particular, neutrino detectors such as DUNE, deep underground neutrino experiment, and the cosmic frontier, which include the CMB, large-scale structure, and also the newcomer, gravitational waves. These studies are also highly interdisciplinary. They lie at the interface of particle physics, cosmology, astrophysics, and gravitational physics. So as mentioned, I will highlight gravitational waves as a probe for new physics in my talk, among other things. This is a particular timely topic. As we know, the LIGO discovery ushered in a new era of observational astronomy. Meanwhile, there are also unprecedented opportunities for probing new particle physics and early universe cosmology. Gravity waves could be the smoking gun to unravel these long-standing puzzles about dark matter and baryons, and provide a unique tool for probing the primordial dark age. Because gravity waves is the only messenger that can travel freely throughout space since the Big Bang, thanks to the fact that gravity is the weakest force. So the research related to this gravity waves is an emerging field that has seen rapid recent growth. So I did this chart by taking some statistics from arXiv, where we put all the physics preprints at. You can see that up to about 2015-16-ish, it's rather flat and about 200 papers a year. But then shortly after LIGO discovery, you see over the years, there has been significant steady increase. In particular, it has drawn a lot of rapidly growing attention in the high energy physics community. So my dedicated efforts in helping to opening this a new frontier started right at the dawn of this transition time around 2016. So another numerics I can show you is that the LISA Cosmology Working Group, for which I'm a member at, grew from 70 members in 2016 to 350 this year. So in the rest of my talk, I will tell you a few aspects of my work on gravity waves as a probe for fundamental physics and early universe. And I'll also briefly mention my work on considering hidden dark sector as solution to the matter puzzles. So this part will be brief, but as mentioned, it's just in the interest of time, is by no means it's less important or less exciting. Then I'll briefly tell you about the impact of this research in the research community at large. Then I'll come to conclusion and outlook. Okay, so let's start this journey about the gravity waves. What is gravity waves? These are the ripples in layman's language. It's the ripples in the space-time, or technically speaking, it's a propagating fluctuation of gravitational fields. Gravity waves was first proposed by Poincaré and then first predicted by Einstein in 1916. But the interesting story is that it actually took 2 decades to establish its existence. If you're interested, you can look at this some historical article which tells this back and forth story. Then the first indirect observational evidence for gravity waves is the energy loss of the observation of energy loss of a binary neutron star system that can be explained by the radiation of gravity waves. This leads to a Nobel Prize in the 90s. Then, as we all know, the first direct detection was by LIGO collaboration and leads to another Nobel Prize, where our Barry is one of the laureates. So you can see it's quite interesting. Between Einstein's first prediction to the direct detection of gravity waves, it took exactly 100 years. Okay. So in this slide, is a simple illustration about how the gravity waves are predicted theoretically. So Einstein equation in GR shows us that space-time's geometry is related to the matter background. So by varying matter distribution, it would cause a fluctuation in the metric. We call this h mu nu, is a perturbation. And based on this, we can construct a gravitational field. And by plugging this into this GR, we can find that gravitational field is governed by this wave-like equation. So this should also remind you about the analogy in electromagnetic wave as shown here. So this is a simple story about how the ripples of space-time were predicted. Now the gravity waves has two physical polarizations, plus and cross. It depends on how it deformed the space-time. And the radiation is also a conical radiation, which means that the system has to violate spherical symmetry. Yeah, just some animation here. Now, to detect gravity waves, we need to measure very tiny effect on relative acceleration of test masses. So this is why the LIGO discovery is so remarkable. It's a very hard experiment. And the detectors depends on the technology, can cover different frequency range and have different level of sensitivity to the strain parameter, which characterizes the strength of the gravitational field, how it can deform the space-time. Now, if we want to see detectable gravity wave signals, we need to look for sources which are dramatic violent events in the cosmos. The familiar example that we heard about is resolvable astrophysical events as observed by LIGO. So these are the transient chirp or burst events that happened at low redshift or billions of years after the Big Bang. But what I will highlight in this talk is that there are also unresolvable cosmological events that originate from very early, very high energy universe. So in case you're not familiar with this, as our universe expand, the temperature cools down. So when we look forward in time, the temperature will drop, but in the early universe, the temperature is quite high, okay? Now, these events can lead to long-lasting so-called stochastic gravitational wave background. It's in direct analogy, well, it's in close analogy to the CMB for EM radiation. So it's a diffuse background. These events that's relevant for the stochastic background production occurred a tiny fraction of seconds after the Big Bang. So it's within this the first second. Now, if we look at the signal in the time domain, we'll see that it looks sort of just like noise, so even harder to detect. But as I'll explain for you shortly, if we can discover it, it will be highly rewarding. It can help us unravel long-standing questions in physics. And this stochastic background is a channel signal that's being actively pursued by LIGO LISA collaboration. And interesting, last year, this pulsar timing experiment that can also measure gravity wave effect called nanograv, they observed an excess that is quite intriguing, and it still needs to be confirmed, but stochastic background from cosmological origin have been shown to possibly explain this success. Okay, so for an experiment, if we want to characterize sensitivity of an experiment to the stochastic background, we often use this thing called the energy density. Omega F has a function frequency that is constructed based on the strain parameter. Now, on the other hand, from a theory, we can predict omega GW with this formula. We can calculate it, and then we can see whether your theory could be within reach of an experiment detection capacity. So this is just to give you a first glimpse of how this omega GW as a function frequency look like, and how some of these experiments, what other sensitivities are. Okay, so now let's look at some concrete representative examples of cosmological sources for this SG gravitational wave background. First, there's inflation, which is a very early era of exponential expansion of the universe that can explain the large-scale homogeneity for the so-called horizon problem, and it can seed the cosmic structure today. The prediction of a stochastic background from inflation is quite generic, but in the minimal model, the signal is usually very small, So we have to wait for the next gen, very futuristic detector to observe them. Now, within better reach of the near future experiments include the source from first order phase transition in the early universe, which can trigger bubble dynamics that lead to stochastic background gravity wave production. This phase transition could be the electroweak phase transition related to the Higgs, and they could also provide the source of the baryon asymmetry. What I will focus on in this talk is on cosmic strings. It's very well motivated, as I'll review for you more shortly, and the signal is potentially strong. So it has been a primary target for both the LIGO and the LISA collaboration. And there's been a continued publication of the official reports. So if we can discover some of these cosmological sources and their gravity wave signals, it's really exciting. This is like listen to the echoes from the Big Bang era through the tools of gravity waves and solve big puzzles. Okay, so now let's start to look at some these cosmic strings as an example. So these strings are one-dimensional topological defects on cosmological scales. They can originate from superstring theory or non-trivial solution of field theory with certain symmetry breaking pattern. For instance, a U1 symmetry breaking, that could be a gauge U1 or a global U1. We'll talk about global case later, but we'll first talk about this gauge case. And we can, for instance, look at the abelian Higgs model, where this complex scalar live in this Mexican head potential. Now, the familiar vacuum solution for this model is that the phi takes the same wave everywhere. But Nielsen and Olsen found that there's a non-trivial string-like solution where the phase of this phi is position dependent, while the wave is 0 at the origin. So this kind of configuration reveals itself as a tube of false vacuum, which could be closed loop or open long string. And the tension of this string is proportional to the symmetry breaking wave square. Okay, so in case some of you think this cosmic string, although it's well motivated, maybe a too exotic object to consider, I want to tell you that there's actually close analogy with a very similar theoretical origin in the condensed matter. That is a vortex in the type 2 superconductor, which has been already observed. So the cosmic strings is certainly not a wild idea, and it's worth looking for. Okay, so how does a string cosmic string come about in the early universe? They are formed through the Kibble mechanism. Essentially, as the universe cools down, it undergoes a phase transition at a critical temperature. And at this point, the phase of this Higgs-like scalar cannot be correlated on scales beyond the horizon size, which is finite. Therefore, the string necessarily formed at the boundary of the causally disconnected domains. Now, if we look into the sky, we would expect to see a few horizon-sized long strings, along with many string loops that are formed by long string intersection. So just to entertain you, this is a simulation video by the cosmology group at Cambridge University to show the string network evolution. Now, if the strings exist, there are many ways to observe them. It's quite rich signals. In this talk, here I will just highlight on this one of the effect on structure formation that was proposed in my paper with Simi and Martin, where we show that this very interesting cosmic filament structure can originate from cosmic strings. And among other things, there's this gravitational wave is the universal signal that I will focus on. Now, gravity waves were emitted from string loops as it oscillates. And if this event, this gravity wave burst event happens at low redshift and resolvable, they would show up as transient signal. But on the other hand, the accumulation of unresolved bursts from high redshift will lead to a stochastic background. Now, the computation of the gravity wave signal from a string network is a complex process. I'm not going to bore you with the technical details here. But I want to highlight 2 points. One is that the emission from the string network is continuous throughout a long epoch of history. Because of this, this source can populate gravity waves over a rather wide frequency range and enables this cosmic archaeology technique that I will introduce to you shortly. Another thing is that to calculate this energy gravity wave signal, we need to integrate over the emission time and also sum over oscillation modes. So as said, you do not need to worry about the details. I will make sure I always emphasize the take-home message so everyone can follow. So the take-home message for this part I want you to take note on is a point from this the final result after we put together everything. The key things to keep in mind is that omega GW, the gravity wave spectrum, is determined, or one of the key factors is this expansion parameter A, which characterizes the size of the universe as a function of t. So as we'll show you shortly, the A as a function of t is directly related to the Hubble expansion rate, its evolution, or the evolution of cosmic history. So this information is encoded in the gravity wave spectrum. This is very important. So in case you're not familiar with, the Hubble expansion rate is defined as A dot over A. By applying Einstein equation in our expanding universe geometry, we can find this relation between Hubble and the total energy density of the background universe. Now, there are 2 important effects that the background energy can affect Hubble, which will be relevant to our later discussion. First, the equational state of the dominating energy composition would affect the relation between Hubble and the expansion parameter. For instance, there's a parallel of -3, -4 for matter and radiation domination, respectively. And another effect is if we have relativistic Hall species, they would contribute to the Hubble in terms of this effective degrees of freedom, relativistic degrees of freedom parameter, GCR, as a prefactor. Now, the first obvious example we want to test is to specify the age as in the standard cosmology based on our assumptions. So here's a quick review of the standard cosmology where this the yellow line is the horizon size as a function of the expansion parameter. So you see in our standard cosmology picture, we have inflation, and then there's a long epoch radiation, and then matter domination. These kinks, as you see here, it originate from what I just told you here because of the change of equational state. So it changed this parallel here. But I also want to remind you that although standard cosmology is cool, but if in the first second is full of mystery. We do not know what happened there yet. Okay, so first in our work, we first calculate the gravity wave spectrum with the standard cosmology. As I've shown you, you plug in the h as a function of t to this formula we derived, then you can find the spectrum. So the spectrum is shown in this solid black line. So a key feature is that towards a higher frequency, there's a long, almost flat plateau. Well, so if you have any deviation from the standard picture, we can see it easily. Another key thing a very important thing we found in this paper is that gravity wave with a given frequency was mainly contributed by loops formed at a certain time or certain temperature. So the cool thing here is that if we look by looking towards the high frequency part of the gravity wave spectrum, we're actually looking back in time to look at the information from the early universe. This is very important because this finding suggests a unique way to shed light on the primordial dark age using gravitational waves. In our work, we quantify this FT correspondence in detail as shown here. Now, let me just elaborate this FT relation a little bit. So it is very important. This correspondence allows us to do this, what we branded as cosmic archaeology. The point again is because, as we have seen, the Hubble or the cosmic history's evolution determines the gravitational wave spectrum. And in turn, in observation, if we observe a certain pattern of the gravity wave spectrum, we'll be able to infer the information about the cosmic evolution, the Hubble expansion parameter. We examine the application of this method in practice. So as we know, the gravity wave experimental coverage now is up to a frequency of 100 Hertz. This, if we consider the FT relation, means that using this method, we can probe the cosmic history from BBN time all the way back to the temperature of 10 to the 4 GeV. Well, BBN is at a mega eV scale. So this is well above the electroweak scale phase transition. So in the last slide, what I showed you was the two slides before was the result when we plug in the standard cosmology. But as emphasized many times in this talk, we do not actually know the history before BBN the first second. On the other hand, the departure from this standard paradigm actually very well motivated. One example is that there could be non-standard equation of state or new phases or alternative cosmic history. This include, for one, the possible early matter domination, which can arise from long-lived particles or primordial black holes, and it has potential relation to supersymmetry, Biogenesis, dark matter physics. Another possible new phase is a kination. This is an era where an energy component is dominated by kinetic energy and is redshift faster than radiation. This can originate from some models for inflation, dark energy, or axions. Now, the presence of any of these new phases would mark a dramatic deviation from our assumption that there's a prolonged epoch of radiation domination. And this kind of departure or deviation actually really matters because recent work has shown that they may have an impact on the late universe, such as the dark matter halo structure and dark matter indirect detection signal. Another way that possibility that the standard cosmology paradigm may see a deviation is the possibility that there may be new particle species which are very generically predicted in BSM particle physics, and there may be even hundreds of them. For instance, as motivated from dark sector solutions to electroweak hierarchy problem. So in general, these new particles could be well beyond the reach of existing means because they're too heavy or too weakly interacting for LHC or CMB. But the good news is that typically they would be in form of radiation in the early universe, and thus contribute to this G-star variable that I told you earlier, the number of relativistic degrees of freedom. And then in turn, as I shown you, it can affect the Hubble expansion rate through its gravitational effect. Now, the next thing we did in our paper is to look at how would the non-standard cosmology change the spectrum from the strings? What's the inference? So as you can see here, the solid line against the standard cosmology prediction. Then we take the benchmark points, assuming that there's a transition from radiation domination to other phases at certain temperatures. So the rising line you see here is a prediction if there's an early condensation dominant era, or the falling line from early matter domination. You see the departure from the standard case is quite dramatic. And the transition point in the frequency spectrum are exactly what we predicted based on the FT correspondence that I introduced earlier. So again, it's a cool way to look back in time with a gravity wave spectrum. Now in our work, we also look into how, what's the effect if we have new particle species. For instance, we assume that there may be new particles arising at a weak scale, helping to solve the hierarchy problem. And consequently, the gravity wave signal would see a falling plateau at high frequency after a certain frequency point. Now, the last example about the cosmic archaeology I want to tell you about is this paper published on PRL on gravity wave bursts as a harbinger of cosmic strings diluted by inflation. So recall that early in this talk, I mentioned that inflation is a very well motivated early era of exponential expansion of the universe, which naturally leads to exponential dilution of any pre-existing content. Now, in case you wonder, the universe today was replenished after this extreme emptiness through the so-called reheating process. So anyway, the standard law that we know for long is that inflation would bury all the relics before it. But in our work, we found a counterexample that's sort of an exception to this standard law. We found that the cosmic strings can regrow after inflation and leave distinct gravity wave signals that allow us to even probe the pre-inflation era. So how is this possible? I don't want to go into details, but the simple reason is that after inflation, the correlation length of the string grows slower than the growth rate of the horizon size. So slowly the string can come back to horizon after inflation and rebuild its energy density and produce signals. So in our work, we work out this distinct gravity wave signals in different channels from this diluted then regrow network of strings. We found that in terms of stochastic background signal, it's suppressed at the higher frequency relative to the standard prediction, the standard cosmology prediction. And the strong constraints on gravity waves based on LIGO or pulsar timing can actually be alleviated in this scenario. Now, the highlight in this work is that gravity wave bursts, which are the transient resolvable events due to the strings, they are usually the subleading signal relative to stochastic background when we look at standard picture. But in this scenario, they can be the leading discovery channel. So this show our result. All right. So that's about the cosmic archaeology with gravity waves to probe the primordial dark age. Now I want to switch gear to tell you about how we can apply gravity waves to probe axion-like dark matter candidates. So this work is done with a chat phone. So axion-like dark matter or ALP dark matter, ultralight pseudo-goldstone boson from a global UN symmetry breaking, and it's a leading alternative to the WIMP dark matter paradigm. It's originally motivated as a QCD axion solving strong CP problem, but generic ALP are also well motivated. There's been a lot of recent interest on this subject. But among all these efforts, a relatively underdeveloped aspect of ALP studies is the implication of ALP topological defects, including cosmic strings domain walls, which are generically indispensable companion of the L particle that most people focus on. The reason is that upon the breaking of a global UN symmetry, the axion goldstone would arise as the light angular excitation mode, while the global cosmic string can form with the same principle that we mentioned for a abelian Higgs model, because the phases cannot correlate on, beyond the horizon scale. Then if there's a discrete symmetry breaking, domain wall can also form. So the cosmic strings and domain wall from axion models can have significant impact on dark axion physics and detection methods. There have been rapidly increasing interest in very recent years. So in our work with Chafeng, our focus is to investigate the gravity wave signal from global axion cosmic strings. This subject is overlooked, but could be a discovery channel. The reason it is overlooked is because by naive estimate, the signal is too small. While the early literature, some of them even suggest that the signal is not detectable, it's too small. So this global string scenario is very different from the gauge or the Nambu-Goto string case that most people studied and I explained to you earlier. For global string, because you also have this very light goldstone, usually nearly massless goldstone modes, their emission is often dominates over the gravity wave radiation. Also, relative to the global local string, the global string tension, this mu parameter has this log divergent that is time dependent. So why are we interested in this small signal of gravity wave gravity waves from global strings? Although we know it, even though we know it's a small subleading channel. Our key motivation is the realization that the rare decay mode could be the discovery mode, as we have learned from, for instance, the Higgs discovery. And also you can say we have copied a lot more axions, goldstones produced, but the detection techniques of those particles depend on how it interacts with the standard model, which has a large uncertainty. On the other hand, gravity wave signal is a universal signal. We know how it works, and it gets more promising as the gravity wave detector sensitivity improves in the coming years. So in our work, using a semi-analytical approach, we calculated the stochastic gravitational wave background from global strings. The most important result we found is that the signal is detectable with upcoming gravity wave experiments, unlike some of the earlier literature suggestion. And our finding was inspired many follow-up works, and including some recent simulation findings that support our result. We also found that the frequency temperature correspondence in the global string case is very different from the gauge case. It allows us to probe even higher temperature, up to 10 to the 8 GeV, much earlier than even the gauge string case. Now, in this more recent work, Chafeng and I investigated the effect of non-standard cosmology and new particle species on the global string gravity wave spectrum, as shown here. All right, so hopefully by now you have seen many interesting examples how we can use stochastic gravitational wave background to probe exciting new physics. But here's a caveat to all this excitement with respect to cosmological stochastic background. The catch is that the stochastic gravitational wave background can also originate from astrophysics. For instance, from unresolved binary mergers that happens at high redshift or when the signal is very weak. So this astro source of gravity wave background is of course very interesting on their own, but in terms of the particle physics or the high energy physics that we want to probe with the cosmological signal, they would could be an overwhelming factor or can cause confusion with this cosmological source. But there's no reason to get too pessimistic. First, if we are lucky, the cosmological signal could be large and reveal itself as obvious excess over the astral background. And in general, this is a signal versus background problem. And we do have, it's not so insurmountable. We do have successful histories to draw inspiration from, such as from the studies of CMB and LHC. Furthermore, as hopefully you have realized so far that if you can discover this cosmological signal, the potential rewards is huge. We can, it can shed light on many of the big questions. So it's worth the effort for this reason. The possible solutions to this concern is important currently developing area of research. Among the several possibilities that people have proposed in this talk, I will focus on the solution by utilizing information in the frequency domain. The key point here is that the astral and the cosmo stochastic gravitational wave background, although they are similar in the time domain, they generally have very different shapes in the frequency domain, so which could serve as a discriminator. Now I want to, speaking of this frequency coverage, I want to show you the landscape of gravity wave experiments in terms of frequency band. So as you see here, today we have LIGO. We also have a pulsar timing experiment covering the frequency over here. Then in between, LISA will be launched in the coming decade. And the CMB, which is not shown here, can cover a range in a much lower frequency range. But you notice that there are some notable gaps. The most important, the most studied one is so-called midband range that lies between LIGO and LISA. There are many proposals for this. So I will focus on the impact of this midband in my talk. Okay, to just give you an intuitive idea about this, the existence of these midband experiment proposals, there are laser interferometer-based experiments such as DeSigo, Tiango, and there's also atomic interferometer-based experiments has been proposed to cover this range. Now, this paper with Barry and Simin, our goal is to conduct a dedicated study on how a future midband experiment can complement LISA and LIGO for improving the sensitivity to the cosmological background and separate it from the astral source. In our work, we did explicit modeling of both the astral and the cosmological sources. And in terms of bigger picture, we hope to help boost the science case for midband experiments from a high energy cosmology motivation. For most of the gravity wave experiments so far, the main driver is astrophysical consideration. So we think this could be a good complement. So our key results include, first, we propose a combined parallel sensitivity curve that shows a generic improvement of inclusive stochastic background against noise. So it's very cool, but I don't have time to show you in detail about this. But I will show you in a little bit more detail about our finding that there indeed can be significant improvement in separating cosmo from astral sources with the help of the midband experiment. So here are some plots showing the results from our likelihood analysis for cosmological, considering different cosmological sources. So first, a cosmic string example. So looking at these plots, you don't need to worry about the technical detail how we got this, but the main thing is that these 2D plots shows how well the certain experiments can be sensitive, can constrain or pin down the model parameters. The red contours, the red shaded regions are the 1 and 2 sigma contours with LISA and LIGO data alone. well, the blue contours with the help of midband experiment. So before I tell you anything, you just look at these plots, you'll notice that visually it's obvious that for most of these panels here, the blue region is much smaller than the red region, which means that the midband can really help us localize and constrain the parameters better. So indeed, we found that there can be up to orders of magnitude improvement in the sensitivity to this string tension in terms of constraints. And in terms of discovery potential with the midband, we can also help break degeneracy and pin down the cosmological model parameters a lot better than with without the midband. Now, this is the example from gravity wave. The cosmological source is early time phase transition. So again, you can just visually you can see that the blue contours are much more shrinked relative to the red contours. So we see again that here the midband can has a great advantage to expand our coverage for the phase transition temperature. And also this the red panel here maybe is the most demonstrating plot here. You can see that with the Lisa and LIGO alone, this red region is all over the place. Well, with the midband, the model parameter is narrowed down to quite much, a lot better. So indeed, the model parameters of the cosmological signals much better localized with the midband data because it allows us to characterize the shape information of the spectrum, which is very important to determine the model parameters. Okay, so that's about the story of gravity waves as a probe of new physics. So now in the last few slides, I want to briefly tell you about my work on related to hidden dark matter sector and biogenesis. Now, as many of you heard about, this WIMP dark matter is an attractive dark matter candidate, but it has been increasingly challenged by data. Therefore, dark matter beyond the WIMP paradigm has been a hot topic. This include the possibility of axion dark matter, primordial black hole, and also a very appealing class model is dark sector, which means that the dark matter physics is now minimal, composed of multiple dark states or even dark forces. This is considering how complex our standard model is, as you see here, this is a very natural and generic possibility. It's a very active area of research. It's a key synergy among the UCR, the faculty in our department in high energy physics, theory, and astronomy. For instance, this self-interacting dark matter is an interesting class of the dark sector models, and Heibo is an expert in this topic. So my contribution in this direction is through systematic classification of thermal dark sector possibilities. Essentially, I look at this diagram of a new realization WIMP miracle, where instead of dark matter annihilate to a standard model final states, it goes to interact with the dark state. And by classifying the possibility of X, we found new avenues for dark matter discovery. So one of the phenomena I want to highlight is this boost dark matter idea that can provide a very new type of signal that can be observed in neutrino experiments. This idea was first proposed in my earlier work, now is highly cited, and is well known in the major neutrino experimental collaborations. The official analysis and ongoing study is done by the Super-K collaboration. It's published, and it's also highlighted in the Dune TDR. We have a chapter on that, and I'm a co-author on this Dune TDR as a member. Recently, with my collaborators including the Dune leaders at Stanford SLAC, we published a paper on boost dark matter search with hadronic interactions. Another interesting channel is the dark radiation. So these are signals that can be observed with dark matter direct detection experiments, CMB, large-scale structure data. So I published a series of work in this topic, including one with a former UCR postdoc, Ran Huo. Now, this last slide about research topic is on biogenesis. Early on, I proposed this mechanism of biogenesis from metastable WIMP decay, or in short, WIMP biogenesis, which is a new mechanism that can simultaneously address the baryon puzzle, the baryon asymmetry, and this baryon dark matter coincidence. In terms of phenomenology, a very generic and exciting prediction from this type of model, it gives a prospect of reproducing early universe biogenesis process in the current day collider experiments in this channel, search channel called long-lived particle or displaced vertex. So the figure here, the left panel shows how the event topology will look like in a collider experiment. And in comparison, you can see that there's if it's a stable WIMP, then we look for it as in terms of missing energy at LHC. So I think it's a quite interesting analogy and equally exciting. So after our work is out, it quickly drew the interest from Atlas collaboration. And this biogenesis model has been adopted by the Atlas long-lived particle working group as one of the few benchmark that they include and actually simulate in detail in their official report that was published in 2019. So while they were doing the analysis, I played an advisory role for their study, and I look forward to helping them more with the future data. So here with my student Michael, I also further developed the model building aspect of WIMP biogenesis, this idea. Particularly, we proposed so-called WIMP cogenesis, where we can, in the same decay chain as shown here, we can simultaneously produce asymmetric dark matter and baryon asymmetry. And there's a rich signal that we predicted, which can be tested. In addition, along with Michael and other collaborators, I also look at new ways to probe other compelling biogenesis models beyond the one that I proposed myself. This include, for instance, testing direct leptogenesis. This is the mechanism that can also relate to the original neutrino mass. So testing this direct leptogenesis by combining CMB observable and terrestrial neutrino measurements. Okay, so that's about the research projects and the result I want to tell you in this talk. So in this slide, I want to briefly tell you about how this research that I have told you about, what's their impact in the research community at large, and how I represent UCR in some of the big collaborations and major events. So as my work on Bootstrap Method and gravity waves were well recognized by the June and Lisa collaboration, I was invited to join June as institutional board member and contributed to the June TDR. I also a social member of Lisa Consortium, and I actively participate in Lisa science book writing along with Chafeng. So as I joined these collaborations, I also officially brought in the members in my research group at UCR. For Lisa, also brought in Simin and some of his group members. In addition, as mentioned, I'm also a theoretical advisor for the Atlas long-lived particle working group analysis. Furthermore, with the goal of help advance the scientific research on these big questions in the bigger community, I've been actually engaged in proposing and organizing major conferences and meetings. For instance, I co-proposed a long-term program at Copley Institute for Theoretical Physics in Santa Barbara, KITP, from inflation to the hot Big Bang. And our proposal was approved, and I was appointed as the lead organizer. and I also co-convened the associate conference last year. So I want to mention that luckily our program was, I think, the last one that was able to finish fully in person before the COVID situation escalated. Then I also co-proposed a workshop on probing new physics with gravity waves at MITP, also a renowned institute in Germany. It should have happened now, but because of COVID, it was postponed to next year. Now, I was also honored to be invited to serve as a member of the American Physical Society Division of Particle Physics Program Committee, in charge of organizing events related to dark matter. In this past April meeting, the APS, I was the organizer and chair of this joint session on new frontiers in dark matter research. So my professional contributions include being invited to serve as panelist or reviewer for multiple programs at Department of Energy, National Science Foundation, and also major funding agencies in Europe. I was also appointed as the editor for the theory summary session and journal corresponding author for this important community report, the white paper on new opportunities at the next generation neutrino experiments, which is organized by the chairs of the Dune BSM working group. Okay, so now let me come to conclusions. As in this talk, I've shown you there are great mysteries that remain about our universe, but we also have very exciting time ahead where we expect to have many great experiments offering great opportunities for discovery. My work is well connected to the big experiments across the different frontiers, including the LHC, next generation neutrino experiments such as Dune, CMB stage 4, LIGO, and LISA. So we'll see expect to see a major upgrade or launching of many of these experiments. So it's very exciting. So my contribution to this endeavor to unlocking these big questions, as I'm discussing in this talk, include proposing new theoretical mechanisms, proposing new experimental search strategies, which have already been having an impact at experiments such as Dune, LHC. And I'm also part of the Gravity Wave for BSM initiative after LIGO discovery, and propose this, I think it's a very cool idea of cosmic archaeology. Now looking into the future, first, I will continue to have direct impact and input for the design and development of major upcoming experiments, and also have a series of ideas to probe new aspects of understanding and detecting dark matter, new ideas on matter-antimatter asymmetry, and new probes, as well as probing other gravity wave sources and dig deeper into the potential of what gravity waves can tell us about new physics. So many of these ongoing or planned projects involve current or former postdoc and students at UCR. Okay, so with this, I would like to wrap up my talk, and thank you all for attending.
Thanks, Yanou, very nice. Questions?
Hello?
Yeah, hello?
May I have a question on your slides about cosmic archaeology?
Oh, let me see. I have several. Am I still sharing screen? Sorry.
Yes, it seems
Yeah.
in several slides you show a figure of.
Right. Hold on. Let me find the. Which slide here?
Yes.
This one.
So
yeah, I have
yes.
Several different plots. Yeah, this one.
So here, do I understand correctly that the theoretical prediction black line correspond to a family of theoretical prediction instead of a single one?
No, the standard cosmology is actually we know the story it's a definite story. So I think I reviewed it here. Yeah. Wait. Hold on. Yeah, this is a standard history where you have inflation and then you have the radiation dominated era up to the familiar matter radiation equality time. So what we did is that this standard cosmology history is a known thing. So we know the age as a function of T evolution. Then we plug this in to find this spectrum.
I see. So,
yeah, so there's a correspondence, one-to-one correspondence between the cosmic history and the spectrum you see.
I see. I see.
Yeah.
So the origin of this feature is because those strings last for a long time.
Yes, exactly. Yeah.
Yeah.
Yeah, that's a key point. I emphasize that different from many other sources, this the string signal is emitted throughout the history, which enable us to populate this wide frequency range.
I see. Very interesting. Thank you.
Thank you. Yeah.
Hi, Bo, did you have a question?
Yeah, I was. So was mentioning about the astrophysical background. You mentioned how to overcome, but if I'm interested in like astrophysical background, like a stochastic, like a gravitational waves, but how likely we could detect it? I mean, so could you maybe elaborate this a little bit more? That
as I mentioned, although the focus of my talk is on high energy physics, beyond standard model high energy physics signal, but the stochastic background from astro sources are very interesting on their own, right? And actually at LIGO, they are having this inclusive search, which it's an inclusive search that includes both astro and the cosmological background. So then if you're interested in the astrophysical source, there could be some finer feature that you can use, like there could be a larger non-Gaussianity in your signal, and people wrote paper on that. Yeah, so there's certainly a prospect of finding this astrophysical source as well.
But for that, maybe I can ask one more related is that I would expect that there's a lot of sources, right? So all the signals will be stacked together. Is there any way like to distinguish? I mean, even including your new physics source, right? So, I mean, you give an example looking to the frequency domain, but is there any other ways? I mean, because I don't have any idea about in this field, but I'm very curious about that.
Yeah, very good question. So I think, of course, you can have this superposition of different sources, which was what we did in the likelihood analysis with Simi and Berry. So yeah, what you can do is that you can have coexistence of astro and the cosmological sources, but you can use this likelihood template analysis to be able to find out what's the weight of each component, right? Okay. Yeah, and I think the main thing is that I expect the first discovery would be excess in gravity stochastic background, and then the question is it astro or cosmological? So that's the next level question. Yeah,
that's
very
true.
good.
Yes. Yeah, thanks.
Any other questions? I had a quick one, Yanou. Just curious, the last item on your last slide about the connection of the baryon asymmetry to large-scale structure.
Oh, yeah, that is an ongoing study.
Yeah.
So yeah, that is an ongoing study where we're considering that although the high energy or the very high scale baryogenesis, like leptogenesis or also gut baryogenesis, usually there's no way to directly probe them because it happens at very high energy early universe. But we are finding a possibility that there's this recent proposal, so-called cosmological collider physics, where you can look into the non-Gaussianity in the primordial perturbation, which can have information about this the interaction between particles in the very early universe. So what we are looking at here is that there could be some high-scale baryogenesis models where the interaction can be probed through this non-Gaussianity signals from the large-scale structure data. Yeah.
Okay, interesting.
Yeah.
Any final questions?
I have a question.
Mhm.
So I just wanted to know, like, how do like specifically primordial black holes would affect this the background this GW spectrum?
The primordial black hole, so first, whether there's primordial black hole is still something that people are exploring. I think Simin probably know more about this. And if they do exist, they would, they can also form a stochastic background through the earlier events. But I would say this would be a more in terms of the cosmic string or phase transition signal that I'm talking about here. The primordial black hole signal would be a background of more uncertainty compared to the astral sources that we consider in the paper with the Simin and Barry. But it's an interesting potential contribution. But for the analysis, the simplest thing to start with to consider some well-defined models and to see how much you can distinguish the two. So you could do the same exercise if you have a certain model for primordial black hole.
Oh, okay. I mean, I just wanted to make a comment there because with these cosmological, with the periods of cosmological phase transition, I mean, they also predict an increase in the formation of primordial black holes, like a era where you're producing a lot of primordial black holes. So every time a phase transition happens, so I'm just wondering,
it's not always producing primordial black hole. It depends. It's
yes,
that's actually also one thing that I'm looking at. Yeah, so that's a possibility. Yes.
Okay.
But it's not always, you do not always have primordial black hole. Yeah.
Okay. No final questions? No more questions? Okay, I think we are done. So let's all thank Yanou again. Thanks.
Yeah, thanks all for attending. Bye.
Bye.